Hello students, welcome to Inside Physics. Here today we are going to discuss about a potential box, one dimensional potential box. This is a topic in quantum mechanics. So here in quantum mechanics we know that the particles are divided into two categories. One is free particles and the second one bounded particles. Free particles means they are moving freely under no external forces. So if you want to study a free particle, there will not be any force, so there is no work done on the particle and the potential will become zero. Here in quantum mechanics, we almost take the study of subatomic particles, because when you come to subatomic particles, the classical mechanics is a failure theory, because see, the subatomic particles moving with high velocities, and you cannot apply the classical principles to quantum mechanics in this way. So the subatomic particles are treated with quantum mechanics process. So in this process, the particles are traced. That means we want to find the position of the particles based on their energies, not by the classical mechanics methods where we use it to calculate the velocity, speed, acceleration, like that. Here we take the consideration in this video for a bounded particle which is bounded by some boundaries, and the space in which it is moving is considered as a potential well, one dimensional. That means one dimensional motion. We are studying the one dimensional motion of a bounded particle, so under no external force, but it has boundaries. That is why it is called a rectangular potential well or potential box. Well means it is not any well, it is a space which has some boundaries, and the particle moving inside the boundaries, and the particle cannot cross the boundaries, but it can move freely to and fro inside the boundaries. So this is called a potential well, and I will draw the diagram for an imaginary potential well where the particle can move to and fro freely. If you take the boundaries, the left boundary as x is equal to 0 and the right boundary as x is equal to L. Inside the boundaries we can find the particle. So there is a wave function, so to trace the particle, and the potential inside the well is 0. The height of the potential well, that means height means it is not the actual height. The potential will reach to infinity at the boundaries. The potential reaching to infinity means the work done for the particle to cross these boundaries will go unlimitedly up to infinity. That means it cannot cross the boundary. That is the meaning. So here at the boundary we cannot find any particle. So here at the boundaries the wave function will become 0. Okay, psi of x will become 0 at the boundaries. Inside we can trace the particle, and the potential inside the well is 0 because it is moving under free conditions, no external force. So here for this scenario we will apply the Schrodinger time independent equation, which we can write it as, see here, dou square psi by dou x square plus 8 pi square me by 8 pi square me by h square psi is equal to 0. So this time independent Schrodinger equation, so we will get the equation, and the solution for the equation can be written as, okay, see, this is what we got here, and for the calculation purpose, to get the easy calculation, I will rewrite this equation as plus, I will take this term as k square Okay, where here see k is equal to 8 pi square me by h square. So for this equation we want to get the solution. This is a progressive differential equation where psi is a complex valued function. So when the particle is moving to and fro, the solution of this equation will become a sin kx plus b cos kx. Why this equation, this solution has come? We can write psi as a function of x. So for this differential equation, the solution can be written like this, because the particle is moving to and fro like an oscillation inside the potential well. Okay. So here if you observe, in this case a and b are any complex numbers and k is the propagation constant. Okay. Here for applying boundary conditions to this solution, see, when we apply the boundary conditions to this solution, this equation becomes the solution at this boundary and the solution at this boundary. So first boundary condition we apply here. First boundary condition. Why we are applying the boundary conditions means we got the solution for the differential equation, and this solution gives the probability of finding the particle at the boundaries and within the boundary. So at the first boundary what happens? X is equal to 0 and psi of x is equal to also 0. Then if you apply the conditions at the first boundary at x is equal to 0, that means 0 is equal to a sin k into 0 plus b cos k into 0. That means a sin of 0 is 0, b cos of 0 is equal to 1. That becomes b is equal to 0. At the first boundary condition, the solution we apply and the b, the second complex number, has come as 0. The same thing we apply for the second boundary condition. What happens? The second boundary condition is x is equal to L. When you apply at x is equal to L also, psi of x is equal to 0. What is the meaning of psi of x is equal to 0 means? The wave function is becoming 0. The function which is actually the representer for the particle is becoming 0 means we cannot find the particle at the boundary. So here at x is equal to L, this equation becomes again 0 is equal to, this equation will become 0 is equal to a sin KL plus B cos KL. B cos KL. See, for this equation I have applied the first boundary condition, which this is the left boundary, this is the right boundary. The particle cannot come to the left crossing this boundary and cannot go to the right side crossing this boundary, and the height of the potential well is also so high so that it cannot escape from the well, because the particle's total energy is far less than the potential height. So here if you observe this equation, we know that B is actually come as 0. Here if you put B is equal to 0, this equation will come as A sin KL. 0 is equal to A sin KL. A cannot be 0, right? If you observe this one, A cannot be 0. Why? Because A is a complex number and A not equal to 0 if you write. What else can be 0? Sin KL must be equal to 0. So if the sin values are equal to 0, this KL must be equal to n pi, where n is an integer. Then only the sin value becomes 0. So here if you observe, k becomes n pi by L. Okay. with k, with this value, the wave equation will become, write the wave equation. What is here, what we got? 0 is equal to a sine, before that what we got? Psi of x is equal to a sine kx. This is the solution where we took b is equal to 0. So this will become psi of x is equal to a sine of k, means n pi x by l. Okay, this is the wave equation where k has become n pi by l. L is the boundary. Okay, so here how to get the value of a? The value of a becomes root 2 by L when we normalize this wave equation. That we will see in the next video how to get the value of a. For now, I will write the normalized wave function as psi n of x is equal to root of 2 by L sine of n pi x by L. See, this is the normalized wave function of this, because when we normalize the wave function, then only the probability density of the particle will be found, and this calculation of the value of a we will see in the next session after completing this process. Okay, so after this we will evaluate the energy of the particle which is moving inside the potential well. As per quantum mechanics, the bounded particle which is moving inside some boundaries cannot have all the values of the energy. So it must have only discrete energy levels. There are some fixed energy levels, and we will find what are the fixed energy levels here. Okay, so if you observe this one, what I have written here, 8 pi square me h square is equal to k. Initially we are taken like this. So by this equation we will evaluate what is E, and the formula for energy inside the potential will be evaluated. So this normalization and finding the value of A will be seen in the later sessions. So for now we will move to the calculation of energy levels as far as the particle inside a potential well is considered. So we can write from this 8 pi square me by h square is equal to k square. Okay, k square. Initially we considered k square is equal to 8 pi square me by h square, and this has become like an equation dou x square by plus k square psi is equal to 0. This is what we assumed in the beginning. Okay, here see k, what we got k here in the previous calculation, n pi by L. So if you put at 8 pi square me by h square is equal to n square pi square by L square. I have taken k value from here. Just I rubbed it off just before, so you can get the n pi by L as k value. You take it pi square by cancellation, and what we get as energy here, n square h square by 8ml square, n square h square by 8ml square. So this is what we got as energy levels. If you observe this equation, the energy of the bounded particle is not only dependent on this boundary, okay, and the Planck's constant, but also dependent on the number n. It is directly proportional to square of the n. This is called quantum number, and the levels it represents are n is equal to 1, 2, 3 like that. These are the quantum energy levels we call, and here with this conclusion we can say the energy levels are quantized. That is what we observed from this equation. What is quantization? Quantization means the particle inside the potential well cannot have all the energy levels. It can only have the prescribed, that means the discrete energy levels, which can be evaluated with this formula. So how does the potential well look like when actually the energy levels are represented? Means we can represent this potential level as E1 first energy level, E2, E3, and we can take it up further at some far place at E4. In this way, the energy levels will go up once the quantum number is increasing. So with this, the first energy level, or we can call it as 0 point energy, the first level will be having with n is equal to 1, it is h square by 8 ml square. Okay. In the same way, for the second energy level, if you put n is equal to 2, it means 4h square by 8 ml square. So 2 times it will get cancelled, and you can directly write h square by 4 ml square. Okay, it is I think 2. 4 by 8, 4 2's. So this is 2 times. Okay. E3, the third energy level will become, if you put n is equal to 3, this equation, the first one, n square h square will become 9h square by 8 m l square. So I am evaluating the energy levels by this formula, which is in the box. Okay, E1, E2, E3. These are the discrete energy levels, but this is not the continuous energy, and the energy of the particle is absolutely quantized. That is what we observed from the process of quantum mechanics, and this is the best method to evaluate the position and the energy levels of the subatomic particles. Okay. So if we apply the same thing to the three-dimensional space, that means the psi function will become xyz, where the coordinates xyz are of three-dimensional space, and this equation will become nx of x into psi of ny of y into psi of nz into z. Okay, so we can write this as psi of nx. So what we can evaluate? Already we have seen psi of x is equal to root of 2 by L into sine of n pi x by L. This is what the wave equation become when we are evaluating the boundary conditions. So in this way we can write here 8 by ABC, where ABC are the boundaries of three-dimensional space. Here 0 and L are the boundary conditions, but here in three-dimensional space ABC are the boundary conditions. So by evaluating for three-dimensional space, we can write this equation as root of 8 by ABC, okay, sine of nx pi x by a, and we'll further write it as into sine of ny pi y by B and sine of nz pi z by c. Okay, so we can write this as in this form. So why we are written like that means the wave function takes the three-dimensional picture here, and the total energy of the particle in three-dimensional picture can be written as, okay, the total energy is equal to E nx plus E ny plus E nz. Okay, so what is here? We know that the formula is evaluated as E is equal to n square h square by 8 m l square. This is what we evaluated, right? The energy levels of the potential box. So with this formula we will conclude the total energy for the three-dimensional. Here nx square h square by 8 m a square plus ny square h square by 8 m b square plus nz square h square by 8 m c square. Okay, this is how we evaluate the total energy of the particle when it is moving in a three-dimensional space. From that we can take the common factor as h square by 8m, that we can take out, and the final equation will become, if you take this common factor as h square by 8m, or I will write in the above column. From this, how I am taking energy is h square by 8m as a common factor. Now this equation will become n square by a square plus ny square by b square plus nz square by c square. Okay, total energy of the particle moving in a three-dimensional space which has boundaries as a, b, c. This is what the process of finding a particle based on the energy levels, and the energy levels, while it is evaluated, we can have the position of the particle inside the space we are calculating. So this is about the potential well. Hope you understood well, and you comment on this video. So what you are expecting from me to have some other videos, you just mention in the comment box so that I can make that videos for you. Okay, thank you.